What have we learned so far? Yeah, that we have learned about 12 weeks in this semester. Mostly we learn about statics, yeah, the study of equilibrium of forces when they are in equilibrium, and also moment when they are in equilibrium. So we have learned in the maybe in the first half of the semester, we learn about the statics of particles. In that case, then we are only concerned about the translational motion, yeah, of the particle. We don't really care about its rotation. We don't really care about the place of the force in relation with the shape of that object. So we consider only that object as a single particle, or if it has a shape or if it has a volume or area, we consider that the force only occurs at the center of gravity of that object. Then after that, we learn the statics of rigid bodies, okay, where we consider also the shape, the size, the dimension of the object in 2 dimension as well as 3 dimension. We learn how to analyze rigid bodies in 2 dimension and 3 dimension when they are in equilibrium. In this case, we need to consider not only translational equilibrium, in this case, the equilibrium of the forces, sigma fx, sigma fy, sigma fz equal to 0 when they are in equilibrium, but since they have shape and the position of the force may be anywhere in that shape, we have to consider also the equilibrium of the moment, so that then the object will not be rotating. Then we have learned also about friction. Yeah, this is non-linear phenomena that occurs in statics. Then we have studied about analysis of structure. So when multiple rigid bodies are connected to each other and they are in equilibrium, so it means there will be action and reaction forces at the interaction point or interaction surfaces. So we have learned about trusses. So when the structures, the system of structure is completely fixed and not non-moving. And then we have learned also about analysis of frames and machines where some part can still be moving. Yeah. And afterwards, we also learn about distributed forces. Now, we consider also that the force may not only be located at the center of gravity, but may be distributed along the surface or along the volume of that object. So to determine the force resultant in 2 dimension, we have also studied 3 different methods for finding the solution. One is the graphical method, where we use ruler and draw to scale, and then find the solution also based on the dimension. Then trigonometry, we can also be used. Trigonometry rules, yeah, using sine and cosine rule, yeah, to find the unknown force. Then something which is also we have been using extensively is the rectangular, using resolving the force into x and y components in 2 dimension, so that then we can solve the equilibrium or we can solve the resultant analytically. So when a particle is in equilibrium in 2 dimension, it means that the resultant of all forces acting on it should be equal to 0. So in this case, that this is of course in force, yeah, vector notation. Yeah? So sigma f should be equal to, which is equal to the resultant force should be equal to 0. In this case, and if we resolve them, if we resolve this resultant, if we resolve each of the force into x and y component in 2 dimension, then sigma fx or rx, the resultant in the x component, x-axis component, should also be equal to 0. Sigma fy equals to ry should also be equals to 0. Yeah. Okay. Then to find or to solve equilibrium problem in 2 dimension, when the sigma f equals to 0, we can also use the 3 methods. Okay. using graphical methods, using ruler and draw to scale. So when it is in equilibrium, then it means the beginning and the end point of the forces, all the forces when they are drawn should be at the same point, because then the sigma F equals to 0, so it means there are no resultant force. Then after drawing the forces in such a way, we can also use trigonometry method using sine or cosine rule to find the unknown force. Or otherwise, in more algebraic method, analytical algebra method, we can resolve the force into x and y component and find the unknown at each axis component. We can use, and what is important here in solving resultant as well as equilibrium, yeah, in two dimension and also later in three dimension, is we have to use free body diagram carefully and consistently to identify all the relevant forces of the particle. Then if there is cable, rope or wire pulley, we should also use free body diagram, and we can use the three methods, either graphical or trigonometry or rectangular components. Then we move to the higher dimension, which is in three-dimensional geometry, three-dimensional analysis. So to solve resultant and equilibrium problem in three dimension, usually we resolve the force into three components within at the three different axes, yeah, of the coordinate system. Usually if it is Cartesian, then it will be x, y, and z components of the force. We can resolve the force component using first angle method. This is if the angles between the force and the three axes are given. So for example, for a single force, we have theta x, theta y, and theta z. Yeah. Alternatively, we can also use second angle method. This is if we are given one angle between the force and an axis, and the other angle between the force and a plane, yeah, and a plane which is formed by the other two axes. Alternatively, the third method is when dimension of the beginning point and the end point of the force are given. So from there, we can calculate then the unit force factor and calculate the x and y and z components of the force. So remember these factor identities, yeah, when the unit factor at x-axis will be equal to lambda x equals to cosine theta x equals to fx divided by the magnitude of the force. Yeah? The fx is the f component at x-axis divided by the magnitude of the force. Lambda y is cosine theta y, fy is the magnitude of the y component divided by the magnitude of the force. Lambda z equals to cosine theta z equals to the fz, the z component of the force, divided by the force. So this is the identity formula, the factor identity formula, that the sum of the square of each of the identity factor at each axis should be equal to 1. Lambda x square plus lambda y square plus lambda z square should be equal to 1. Or in different way, square of cosine theta x, cosine square theta y, cosine theta z square equal to 1. Or if we put this value into this value, okay, we will obtain that the Pythagoras theorem, yeah, the magnitude of the force should be equal to the square root of the sum of the square of individual axis component. So lambda here is the unit vector along the line of action of that force. So in 3D analysis, when we want to calculate the resultant of various forces acting on a particle, then we can first express each of the force in terms of the ijk component forces. Yeah? So R the F1, for example, equals to F1 xi. Yeah, this is a unit vector at the x-axis. Yeah, plus F1 y times j and then f1z times k. Then we can calculate the resultant at each axis. So where then the resultant is sigma fx at I times I plus sigma fyj plus sigma fzk. So the I component here is Rx equals to sigma Fx, and J component Ry equals to F sigma Fy, and K component Rz equals to Fz. Okay. When it is in equilibrium, we just equate the equation to become zero. So the R, the resultant should become zero. R equal to sigma F should become zero. So sigma Fx I plus sigma Fyj plus sigma Fzk should be equal to zero. Since these three factors are perpendicular to each other, so they do not basically influence each other. So it means sigma fx should be equal to 0, sigma fy should be equal to 0, sigma fz should be equal to 0. So this is similar with two-dimensional analysis, only we add one single axis more, one single additional axis. Okay, now when we consider that the object where the force is exerted on has some dimension or has some shape, yeah, has some size, then we have to consider the moment as well. So, for example, like this, when we put a force onto this pen, it is not only depending on the position of the force. Yeah, when we put it at the center of gravity of the pen, then of course it will only move translationally at one single axis. However, if we put it at some point, yeah, not at the center of gravity, what will happen is not only that this pen will move translationally, however, it will also move rotationally. So this pen will rotate, yeah, along its motion, along its translational motion, it will rotate as well about its axis, which is basically the center of gravity or center of centroid, the centroid. Okay? So the rotational motion here is determined whether there is a moment happening on that object. So the moment of a force about a point, about the center of the axis here of the rotation, is defined in two dimensions here by mb equals to f times d. D here is the distance between the line of action of that force towards that point, the perpendicular distance. According to Varignon's theorem, which we have learned during this semester, the moment of a force about a point is equivalent to the summation of the moments of that force's components about that point. Using this theorem, it means that we can resolve a force, for example, if we are having difficulty to find the distance from that line of action of that force to a certain point, about certain point, then what we can do is we resolve first that force into the force component about at certain axis in that two dimension, and then calculate the moment due to each of these force components. Then the sum of the moments due to this force component will be equal to basically the moment due to the original force about that point. This is what Varignon's theorem is about. So we have basically learned it, and we have done many exercise on that. Then there is principle of transmissibility. So the principle of transmissibility states that the moment of a force about a point is the same as long as the force lies on its line of action. So this states, for example, if we have this is a point A, there is a force here. Okay, so its line of action is, of course, this is the line of action, right? So whenever you move this force, as long as that movement is still within this blue line of action, then the moment due to that force about point A will still be the same. So the distance will be this perpendicular distance. So this will be the d. So it means that the moment at about point A will be equal to the force times d. This is in two dimension. Yeah. So this is what the principle of transmissibility states. So it doesn't matter whether you move it along. So perhaps, for example, you move force to here. So which, as long as it has the same magnitude and within that same line of action as the original force here, so it will create the same moment about point A. Okay, so this is what principle of transmissibility is about. Okay, now getting more difficult in 3 dimension. So how to calculate the moment of a force about a point in 3 dimension? So in 3 dimension, then you need to use cross product. Okay, so in this case, we review again the concept of cross product. The cross product is the multiplication, basically, of two factors, and the product of the two factors will be perpendicular to the plane made by that factor, and the direction of that product will be according to the right hand rule. So for example, in this picture now shown in the slide, if we are to calculate P cross Q, so P cross Q, it means then the direction of the direction of the product factor will be towards the screen, right? Toward the screen, away from us. However, when we make a cross product Q cross P, okay, Q cross P like this, so the direction will be towards us or away from the screen. So P cross Q will be towards the screen, away from us. Q cross P will be away from the screen or towards our direction, which is in front of the screen. But the magnitude is the same, which is P, the magnitude of P factor P times the magnitude of factor Q times sine theta. The theta is the angle between the two factor. So from here, then we know that since even though they may have the same, magnitude, but since they have different directions, so according to the concept of vector, when two factors having different direction, of course they are different vectors. So in this case, P cross Q is not equal to Q cross P, okay? Even though the magnitude might be the same. So from here also we know that if P cross Q is parallel or at the same line of action, then the cross product result will be 0, right? Because sine the theta, the angle between them is 0, and sine 0 is 0. We review again the concept of dot product. So in dot product, the result is non-vector, but a scalar. It is a scalar, so a number without having any direction. So P dot Q will be equal to PQ, the magnitude of P times the magnitude of Q times cosine theta, where theta is the angle between the two vectors. And Q dot P equals to magnitude of P times magnitude of Q times cosine theta. So since there is no direction implied in the result, okay, PQ cos theta equals to PQ cos theta, right? So P dot Q equals to Q dot P. So here the commutative law works for dot product result. So because direction is not associated. Okay, so here we have some exercise here. Yeah. Let's have some exercise. So this is basically what we have learned so far in the until this week, until week 12. So next week we will start to learn or to study new concept of parts of mechanics, but not anymore statics, but instead go into part of the dynamics already. Okay, so